Hello, everybody. My name is Ingrid Hotz. I'm from Linköping University in Sweden, and I'm going to share the session, which is the second star session of the conference. So in this session, we will have two stars, with both are concerned with topics that include a large body of work that is also published outside of the visualization domain. So I think these are especially interesting and relevant topics for us here also. So welcome to the session, and we will immediately jump to the first talk, which is on the state of the art of spatial interfaces for 3D visualizations and their interaction techniques. And the talk will be given by Lonni Besançon. So Lonni, please go ahead. The stage is yours.
Hi everyone, I'm very happy to be here today to present this survey on spatial interfaces for 3D visualization. I would have been happier to make this presentation live and go for some drinks with friends after, but we have to adjust to the pandemic situation, unfortunately. Anyways, this paper is the result of a collaboration with Ynnerman, Lingyun, Daniel Keefe, and Tobias Isenberg, and myself, of course, Lonni Besançon. I think all of these photos were taken pre-COVID, and looking at what lockdown has done to me, I'm not sure you can trust these mugshots too much. But anyway, I would argue that there are a couple of terms that we have to clarify from this title. And that's what we mean by spatial interfaces and what we mean by 3D visualizations. So the first thing to clarify is what we mean by 3D visualization. We essentially mean all tasks involved in the sense-making process of 3D datasets that are omnipresent in a variety of fields such as architecture, 3D printing softwares, spatial dataset exploration, medical datasets, and many others. I will not try to make an exhaustive list here. But what is so particular about 3D visualization is, well, that unlike 3D interaction, the goal of 3D visualization goes beyond simple 3D manipulations that have been a huge focus of research in the HCI community. It should include and support more tools for users to be able to understand and derive insights from the data, such as cutting plane manipulation, specific widget placement, or 3D selection of volume of interests. For instance, you can see here a fluid dynamic researcher visualizing a cut through a 3D dataset and manipulating setting point placement in the volume to understand the flow in the original dataset he is looking at. But if you hear 3D interaction and perhaps even 3D visualization, you might think, yet another survey paper on 3D techniques. And it's true that 3D interaction has been the focus of many surveys in the past. However, none of them quite address the focus that we have set out to present today. Let's quickly review why. This survey by Chris Hand was published more than 20 years ago and solely focuses on 3D interaction techniques. So it's quite obviously not up to date, but it also does not address the specific challenges and needs of 3D visualizations. Christian Oliver's work is now 15 years old and only focuses on camera control. Much like other 3D interaction techniques, and the survey focusing on them, camera control is useful for 3D visualization tasks, but it is not sufficient. Some surveys did focus on interaction for data visualization, but they focused, for instance here, with Peniel and Roberts' survey, on a single interaction paradigm, which is here haptics. While this survey here focused on meter gestures. This other work by Jankowski and Ashe is more recent, but focuses only on 3D interaction techniques and not on visualization needs in particular. And the same thing can be said about a survey by Mendes et al., who focused on object manipulation. This is again needed for 3D visualization tasks, but not sufficient. Finally, this last survey focused on medical flow data, which is a specific kind of dataset that is related to 3D visualizations, but the survey does not explore how interaction can help in that regard, and instead focuses on data generation and its analysis. Now it's time to explain what we mean by spatial interfaces. We basically mean paradigms that help propose 3D techniques for 3D interaction, such as tangible interaction, touch interaction, or media gestures. We also include combinations of these paradigms together. Now, why do we focus on these? Well, as I said, a myriad of techniques for 3D interaction have been developed with these, but also they are readily available with off-the-shelf devices, such as mobile devices or simple infrared cameras. Mobile devices can even already be used as a combination of touch devices and tangible devices. But before we dive into the heart of the survey, let's quickly check why these interaction paradigms are interesting. Touch interaction first. It is precise, it is fast, it gives a feeling of direct manipulation, and can be augmented with pressure sensing or multi-touch interaction to provide a richer interaction technique. Tangible interaction now. It is fast because it mimics the way we interact with the world in real life, it has specific understanding value, and it is good for collaboration scenarios. Devices have to be either optically tracked with a proper dedicated camera, or the camera of a mobile device that you can see here, or it has to contain some sort of internal sensors in order to manage to locate itself, just like some mobile devices now do by combining the camera and internal sensors. With mirror gestures, which also mimic the way we interact in the world since movements are inherently 3D, one of the great advantages is that hands are kept free, which is useful in some specific scenarios, such as the one of an operating room that we can see here. Tracking of the hands is either passive with optical tracking, as you can see, or it can be active, as visible here with a specific hand-worn device such as a glove. We finally consider hybrid interaction paradigms. You can see here a combination of touch and tangible interaction, for instance. It helps alleviate the inherent drawbacks of each single interaction paradigm and combine the benefits. So these interaction paradigms are the first axis that we use to categorize the work we surveyed on spatial interfaces for 3D visualization. But what is the other one? We decided to look at visualization tasks to categorize each paper we surveyed. Why is it important? Because it would allow us to see if a specific subcategory of task has not received enough attention, for instance. There are once again many papers proposing classification of tasks in EuroVis or 3D interaction. However, they do not really consider that 3D visualization does introduce some special requirements for interaction tasks, as rightfully pointed by Keefe and Isenberg. As we mentioned earlier, simple manipulations are not enough. To understand, for instance, the internal structure of a dense volumetric dataset, as we can see here, right? Similarly, 3D object selection techniques are unlikely to help researchers select line in a dense 3D dataset such as this one. So what tasks did we focus on? Well, first we consider the essential task of view and object manipulation. So a single viewpoint is rarely enough to properly analyze and understand a 3D dataset, consequently offering the possibilities to manipulate either the viewpoints or the datasets to offer several perspectives becomes essential. But beyond this, many 3D datasets suffer from occlusion. The internal structure of the data is initially not visible to domain experts. So instead of focusing it only on object manipulations, such as the one used in HCI, this task that we decided to have include also cutting plane manipulation that will help reveal the internal structure and properties of the data. Beyond simple object manipulation, scientists looking at 3D datasets have been reported to often make use of axis-constrained manipulations. So we report in this survey whether techniques allow for such constrained manipulations or not. Simply looking at the data is often not enough for domain experts. They often need to rely on specific widgets to explore the data beyond cutting plane and internal structures. Scientists make use of many different widgets. You can see here sitting points that are basically weightless particles that will follow the flow within a dataset in order to help scientists understand vector fields within the data. Many other widgets exist, and their use is essential to explore 3D datasets in many different fields. That is the second task we focus on. Finally, the last task we consider is 3D selection and annotation. 3D selection techniques developed by the HCI community, as we earlier mentioned, are unlikely to work in molecular visualization or dense line datasets. Very often, HCI techniques help select a single object, and you can imagine that selecting atoms one by one would be a very tedious process. We link annotation to this task because it either requires the annotation to be positioned in 3D or it is attached to 3D selection very often. So this finally constitutes the two axes that we use for our survey. We surveyed a total of 134 techniques that we found with a Google Scholar search and following trails of citations. So now I'll try to give you a quick overview of the papers we have found and some of the interesting techniques and findings from there. Let's start with touch interaction. We have a total of 33 techniques that we found with our survey. If we consider the first task of view and object manipulation, we found 90 techniques that allowed it. One of the issues with touch interaction is that it is inherently 2D. While we want to be able to manipulate objects in 3D, that includes rotation around all axes, translations along all axes, and sometimes zooming as well. The HCI community solved this issue with the help of different mappings, such as the following one. 2 fingers manipulation are used for X and Y translation, and they are also used to provide Z translation, which can be assimilated in some cases to a zoom operation with the pinch to zoom technique that is now very common on smartphones. 1 finger manipulations are mapped to XY rotations, and finally rotations around the Z-axis are provided with 2 fingers as well. But what has been done for specific visualization purposes? One technique we used a lot in visualization project is the T-box technique, which is a widget to facilitate 3D manipulations with multi-touch gestures. 1 finger manipulations along the edge of the cube translate along the parallel axis. 1 finger manipulation on the side of the cube controls single axis rotations. Scaling is controlled by pinching the cube. Other techniques have used the 3D axis in the scene to help define axis-constrained interaction. For instance, a 2-finger touch was used to define an axis along which subsequent manipulations will be constrained. Here you see the FI3D widget, which is another widget to provide such manipulations. So translations around the XY axis are initiated with a single finger interaction in the central space. XY rotations are initiated with a single finger touch on the frame and a drag into the center visualization region. Touching the frame with a second finger during this interaction constrains the rotation to single axis depending on the frame. Rotations around the Z-axis are controlled by dragging a single finger along a frame. Some researchers also focused on providing dataset-specific interaction technique. You see here the power of 10 ladder technique. It facilitates exploration of astronomical datasets, which require rotation and scaling operation that span large magnitudes. 2-finger input activates a ladder widget, where each region corresponds to a power of 10 zoom level. The technique also provides classic panning with 5 fingers and rotations with 1 finger. Overall, we find quite a lot of different techniques relying on different widgets or specific gestures to provide 3D manipulations. What has been done for visualization widgets manipulation now? The problematic thing about visualization widget is that they need sometimes to be positioned in the 3D volume. When they don't, such as for drilling cores positioned at the top of a topological map, simple gestures or widgets are enough. When 3D positions are needed, things get more complicated. The technique you see here relied on a combination of gestures and a dual view. The view on the right is the unprojected view from the cutting plane that is positioned on the left. Experts can use the view on the right hand to position visualization widget onto the cutting plane that is in the dataset. To position a finger, give the XY positions at the intersection with the cutting plane provide the depth information that is missing from touch interaction. We only found 3 techniques that propose to have visualization widget manipulations with touch. What about 3D selection now? Again, the third dimension is missing, and that's a bit problematic, but research work has found ways around it. One way around this issue is to rely on a computer to provide the third dimension. Let's imagine that the user draws a lasso to select a part of the dataset. The computer can simply extend the lasso into 3D, but this might also select parts of the data that are not of interest to the user. So more sophisticated approaches have been designed which rely on the properties of the data to assist the user into making a selection volume from a 2D lasso. You can see one of them being used here that rely on the density of particles to provide a selection. If there is some void between 2 objects that would be selected by a simple 3D extrusion of the lasso, the technique is smart enough to not consider the other object, because it relies on the viewpoint use and the property of the visualized data. An alternative is to rely on several steps, which will produce a selection based on the viewing angle, the structure, and the slice of the data that is shown. Most of the techniques we have found rely on the properties of the data to facilitate 3D selection and overcome the 2D nature of touch input for selection. And overall, touch input is mainly limited by its inherent 2D nature. It has been overcome with specific techniques that are often, however, data dependent. Still, touch interaction provide fast and precise manipulation, easy access to widgets and menus, and has naturally constrained manipulation which are often helpful for 3D visualization. It was therefore the focus of a variety of research papers. It is actually the second most investigated paradigm among the paper we surveyed. Now on to tangible input. We said earlier that tangible input is great to mimic live interaction and has therefore been the focus of a lot of work for 3D manipulation in HCI. How has it been used to help visualize spatial datasets? First, let's look at data and cutting plane manipulations. Since the pioneer work of Hinckley and colleagues in '94, many specific tangible props have been designed to assist the manipulation of data and cutting planes. Some decide to use props representing the data to visualize, as you can see here. The benefit of using a prop representing the data itself is that the prop can give users a sort of world in miniature version of the data, and all the manipulations of the props are simultaneously happening in a digital world. Other approaches just use more generic props to avoid having to generate many different props for many different datasets. Here you see a pen being tracked by the tablet to help manipulate a cutting plane of the data that can be manipulated with the cubohexagon that you see in the background. And in specific AR and VR environments, controllers developed with commercially available software can help serve as tangible controllers that are very versatile and generic. Interestingly, props like paper can also be used to see different views of the data through the manipulations. You see here that the paper-like prop is used to navigate between different anatomical views. One of the nice advantages of tangible interaction is that it can allow concurrent manipulation of either multiple parts of the data or of data and cutting planes at the same time, for instance, as you can see here. Another one is that users can use tracked flexible materials to provide non-planar so-called cutting planes of the data. Some tangible devices also facilitate less visual-oriented exploration tasks through active haptic feedback. For instance here, haptic forces are used to represent and simulate molecular interactions. There are really quite a lot of approaches for data and cutting plane manipulation, even more than with touch input. But what about visualization widgets now? We have found a couple of techniques that are proposing some of these. Most of them rely on pointing, either with a specific or generic device, to the 3D location where the widget should be placed. In this first example, the pen allows users to do it. And in this example, the author used a Wiimote, the self-track controller from the video console Wii from Nintendo, to position a sealing point. While in this example, the author allowed the placement of trim ribbons to explore and understand the vector fields of flows around an aircraft with a phantom device, in order to benefit also from the haptic feedback of the device to help guide exploration and positioning of the ribbons. We still did not find a lot of different techniques supporting what we call visualization widgets. How about 3D data selection and annotations now? Devices providing haptic feedbacks have been studied and seem particularly interesting for selection in dense datasets, for instance. They can also allow users to draw selection shapes in 3D directly from which the selection volume will be derived. More generic props can also be used, as you can see here, with basic AR markers moved around to help select part of a brain. In many cases, the track prop can also directly propose to annotate selection through direct manipulation. While this might not be ideal for note-taking, for which it's usually easier to have a plan to write on, it is particularly interesting to draw some annotations and sketch some input or ideas. Tangible interaction was overall the most investigating paradigm that we found. This can probably be explained by the inherent 3D nature of tangible devices that seem to make them, at least in theory, very well suited for 3D visualization tasks. Now let's tackle meter gestures. Meter gestures are particularly suited for some specific domains that require hands to stay free or sterile, such as surgeries and medical applications. While moving hands is generally done in 3D, specific gestures have to be thought of in order to provide clutching mechanism or to disambiguate which object should be moved and when. Therefore, past approaches relied on a combination of unimanual and bimanual gestures. Let's start with data and cutting plane manipulation techniques. In this first example, surgeons can use one hand to manipulate patient data in the operating room, but using a single hand limits what can be done in terms of data manipulation and analysis, although it seems realistic during a surgery that a doctor is not going to take their time to perform a full data analysis. To provide more data manipulation possibilities, having bimanual gestures is a good alternative. For instance here, they use the number of hands and the way they are presented, clenched fist or open palm, to distinguish between several manipulations such as zoom and rotation. More expressive gesture can also be used, of course, and some of the approaches we surveyed decided to look at this. One notably defined a gesture to crack open a dataset instead of using cutting planes in order to look at the internal structure of the data. We overall did not find a lot of different techniques, but since the number of papers that we found with mid-air gestural interaction was also smaller, this seems to make sense. Unfortunately, our survey did not uncover a lot of approaches to manipulate visualization widgets. While most of the developed applications that we have found for the first task of data manipulation do provide the ability to select some visual widget to browse through several 2D slices, for instance, we only found work proposing to measure the distance between 2 points, or to find specific values in a dataset. Similarly, we did not uncover a lot of work addressing 3D data selection beyond some quite basic techniques. One is the manipulations with the hands of predefined selection primitives, such as the cube visible here. Beyond this rather simple and not always convenient selection mechanism, brushing with gestures have also been proposed, as well as annotating directly with one's hands. This approach seems to more directly leverage the benefits of mid-air interaction and would probably be very interesting to study further. So to conclude on mid-air gestures, I would argue that very often the choice between interacting with a single hand or two hands will be constrained by the application domain itself. Mid-air gestures have very often been investigated in a medical domain for obvious reasons around the sterile environment, right? But beyond this, the inherent expressiveness of mid-air gestures shows promises for 3D visualization tasks. So we have now quickly surveyed past work on touch, tangible, and mid-air input to facilitate 3D visualization tasks. Each paradigm shows interesting advantages. Touch is very good and natural to provide constrained interaction and easy to access widgets. Tangible interaction mimics real-life interaction and can sometimes be malleable and provide less generic cut-through data. Besides, tangibles are also very intuitive to provide 3D data / point selection and annotation. Finally, mid-air gestures can be extremely expressive and allow users to stay in a sterile environment. All of these benefits can be combined through hybrid interaction techniques. Surprisingly, such hybrid interaction paradigms have received very little attention according to our survey. Let's review some of the approaches that we have found. Let's start with view and object manipulation techniques. To provide hybrid interaction, mobile devices are particularly interesting. They are nowadays capable of tracking their own manipulation, and they readily provide a touchscreen. Some approaches propose to combine free and intuitive manipulation of the mobile device to potentially constrain touch manipulation. Data in connect planes can therefore be separately manipulated in that way, as you can see here. Other researchers have imagined specific devices that would offer tangible and touch affordances, as you can see here, so that the cube can be moved as a tangible device, but you can also touch the surface to use it as a touch device. Most of the approaches that we found for data manipulation propose to combine touch and tangible interaction through off-the-shelf devices. What about visualization widgets now? When it comes to manipulation of visualization widgets, researchers have proposed again to rely on combinations of touch and tangible interaction from a mobile device, or to make use of specifically designed tangibles combined with touch surfaces, either mobile devices or touch table. You can see here one device that was designed by researchers in order to interact on top of a tablet. Again, the pool of technique we found for visualization widgets manipulation is extremely small, unfortunately. What about 3D data selection? Here again, the idea to combine touch and tangible interaction is interesting. One way to overcome the inherent limitation of the 2D input provided by the tablet is to move the tablet to extend the lasso into 3D. So you can see here the lasso being drawn, and the movements of the tablet are going to extrude this 2D shape into a 3D one that will provide the selection volume. Another way, as imagined here, is to use ray casting from the fingers in order to select what is within the manipulated cube. It is not surprising that most of the approaches that we have found rely on a combination of touch and tangible input, which are readily available with mobile devices. Some other approaches have worked to combine voice input to touch or tangible input to validate commands, for instance, but overall the vast majority of hybrid interaction approaches were combining touch and tangible manipulations. So we have now briefly surveyed the work on interaction techniques for 3D dataset, but what can we learn from the exploration of all of these approaches? The breakdown of past research on interaction paradigm and visualization tasks that you see here is interesting, but the choice of interaction might also depend on what technology is used to render the dataset, or in what environment. We therefore also propose a table breakdown that includes all of the output environments and a combination that you can see here. The color is used to encode the output used for each paper we surveyed. And to facilitate reuse and analysis from the community, we made the data easily available on our OSF repository so you can filter and further analyze the papers that might seem relevant to you without having to click on many different references and scroll through the paper countless times. When possible, we also link to open access versions of the papers too. But let's come back to this table quickly now to try and get some interesting insights. One quick finding is that tangible interaction and touch interaction, to a certain degree as well, have received a lot of attention, while other interaction paradigms, such as meter gestures, seem to not have been explored as much, although they seem to present interesting advantages as well. But beyond this, what is really striking, I would argue, is the lack of focus on manipulation of visualization widgets. This could be partly explained by the fact that the HCI community is not as likely to be aware about the needs to focus on this as we are in the visualization community, for instance. But more interestingly, with some co-authors, including a researcher in fluid dynamics who has also used the system that we developed, we have argued in the past that the fact that researchers in Viz and the fact that they don't provide a system supporting all the needs of domain experts that would integrate also in their workflow could very well explain the lack of adoptions of our tools and techniques by domain experts. Another exciting venue for future work lies in the use of interaction to help inform the public. Interactive exploration of data is beneficial to experts, but also has been argued to help in outreach and science communication overall. However, only a couple of the works that we have surveyed focus on providing intuitive interactions paradigms that could be used in the context of public activities or places to communicate about scientific discoveries, such as museums. On this topic, my co-author Anders would be happy to explain the idea of exploration and all the initiatives done at the Visualization Center in Norrköping, where Anders has been actively working. Another document we put online for people to explore is the breakdown of which paradigms were used by hybrid interaction techniques. I have mentioned it multiple times, the focus on tension tangible is logical. However, other combinations should surely be investigated, and we hope that we have managed to stimulate interest in this regard. What about tangible and media gestures, touch and voice, or even a combination of more than two paradigms? This is rarely a vision, and one can argue that it should be. Finally, one last challenge and avenue for future work that we argue for is evaluation. This is particularly relevant for spatial datasets and research around them. We often have to focus on specific domain and therefore ask for inputs or evaluation from domain experts who are, by definition, not many and not necessarily available for long and repetitive evaluations. I assume that many of you are familiar with the Believe workshop on going beyond time and error in visualization techniques and their evaluation, but I guess it's always good to point to this initiative now anyways. We found that some papers relied instead of on use cases or on in situ evaluations, for an example with surgeons during real procedures, which I think is extremely promising and exciting. Some researchers in the field have argued before that perhaps we should not rely solely on evaluation to accept and reject papers, and that sometimes publishing without evaluation would help spark some creativity in the domain. I would tend to argue that it would be fine to do so as long as authors don't make claims about the efficiency of their technique. Similarly, it was extremely difficult to find mentions in all of these papers of which system were successfully adopted by domain experts. And newspaper pieces often report that AR/VR visualization softwares are helpful, but they rarely cite the work that we do. And making a piece of software robust enough for domain experts is time-consuming, and considering the whole publish or perish paradigm in academia, it is therefore unlikely that researchers will spend tremendous efforts to make it happen, as they would not get any direct benefit for it career-wise. But in the medical field, for instance, doctors can report on unusual cases with what is called case reports. Perhaps we could just adopt case report to mention successes and failures in trying to develop for domain experts. That might be a way to solve this issue by giving incentive to spend more effort in developing for domain experts, because we then provide the opportunity to publish about it. One last explanation of why our work might not be adopted is the fact that the code we have is not necessarily shared by default. With co-authors outside of HCI and visualization, last year we argued for the benefits of open science quite strongly while looking at COVID-19 research, at its lack of transparency and what it led to. While in our field the consequences of a lack of transparency are surely not as dramatic, it would still be beneficial to make it a habit to link to source code for others to use, reuse as baseline for studies, or for fellow programmers to improve on and therefore perhaps foster adoption of our techniques by domain experts or other users. On the topic of open science, the preprint of our paper contains a link to the open access version of all references whenever possible, as you can see here highlighted in bold. Clicking on open access should lead you right away to a non-paywall version of the reference. All the credits and references from this talk are detailed here, and the list will be posted on our OSF repository. So that's it for me. Thank you very much for your attention. You can find the paper and all our materials online. We'll be happy to take your questions now.
So Lonni, thank you for your very interesting talk. I have immediately some questions while I'm waiting for some questions from Discord coming in.
Sure.
So you presented 3 different classes of tasks, like this object manipulation, 3D selections, and so on. However, in many cases, the tasks that we are looking at in visualization environments are much more complex. How do you think do the methods that you presented here scale to more complex tasks? Like, for example, if you have kind of 1D and 2D selection integrated in your system.
Yeah, right. So it is, we looked at a lot of different classification of tasks and visualization and tried to see like which one we could use for our survey. It's a little bit difficult to actually find one that you can use for the specific case of 3D data sets, because there's really a lot. I mean, beyond the whole classification of 3D tasks for just manipulation, there's also the ones just for this. So we tried to breach that. It was a little bit difficult, and I agree that in many cases, the end goal of something that we're doing is going to be like a combination of all of these tasks together, the one that we presented here. So it's quite unclear how the techniques that we surveyed would actually scale to this, right? Like, because very often, in particular, as we saw during the survey, like the techniques that have been developed will just really focus on providing a manipulation of an object or of a data set or a cutting plane, and they really go beyond this. And it's one of the issues that we actually try to highlight here, is like, if we want whatever software we're developing to be adopted in the end by domain experts, I think we have to focus on this like very high level task that they try to solve, because so far it's very unclear through like reading papers how that would scale to more complicated tasks, or even like how that would integrate to a specific workflow. So we don't have any insight on this because very often there's none directly in the paper.
Thank you. So I also have a question from Discord now. So from Noska, she says, I see many extremely cool interaction techniques, and you also mentioned that they hindered uptake by the domain users. Do you have any thoughts about what could be in the way, specifically in the medical domain?
So I guess you mean like what could be in the way about like for them to adopt it, right? I guess what not I mean. I don't know. So while looking at what kind of techniques were like successfully adopted by domain expert, I've seen really a lot of different press articles about how VR is helping doctors to plan surgeries and all of these things. But it was very difficult to actually know which system they were using. If it was part of a research project, or if it was part of something that was developed privately for the hospital, the team of surgeons that were using it. And that's one of the things we tried to highlight in the survey there. It's a little bit difficult to know if they use the things we developed directly, or if they just rely on private contractors to develop something that's specifically needed in the end for the things that actually make it to the press. For doctors in general, why they would use or not use or adopt something, it's a little bit unclear as well. I think there's lots of regulations also around like what kind of procedures they are allowed to use in a hospital, and it needs to go through regulations and approval from specific organisms before it could be used. So I think there's a bit of that as well. But we did find one paper that was quite interesting actually, where I think it was for some kind of like surgery of kidneys or something like this, where actually the authors of the paper tested this with surgeons in the operating room, which was actually very nice. So they didn't go into measures of like efficiency, like time and errors and all of these things, but they actually asked surgeons to try and use the tool they had in the OR, which was very cool stuff, I think. So I don't know, going through all these papers, I think one of the things that I would have liked to see is maybe more of these kind of work, like maybe asking when possible, like domain experts directly use it in like really hands-on situation, not just in the lab and everything. But yeah, it's a little bit difficult to know what's stopping them.
So Gao is asking whether you could elaborate more about why task group 2 is less explored, like defining, placing, and manipulating visualization widgets.
Yeah, that's a great question. I'm not sure I have the answer. We hinted to some of the answers in the talk. I think in many cases, the techniques that we have, there's always an overlap between the Viz and the HCI community. And the techniques that are developed for 3D data sets and 3D manipulations come with that mix of the two communities, right? And it's a little bit, I think in many cases, people that are more HCI oriented don't know that this is a specific need to have visualization widgets they can just put in the data to understand it better. Because it seems that very often when you look at 3D data, all you need to do is actually look at it and maybe get a cutting plane view of it, and you would be able to understand it. But once you work with people that actually work with this kind of data, you realize there's way more to it than that. And including as well, like the ability to run scripts on the data to highlight some specific things and all of this, right? When I started my PhD, I actually worked with fluid dynamic researchers, and like I could see that the way they deal with their 3D data is they have a MATLAB script that they run that's going to place sitting point in 3D somewhere. And then every time they want to change it, they need to change the script. So quit the software, change the script, change the position of the sitting point, run the script again, so on and so forth, right? And so that's why I focused on something in particular with sitting point placements in one of the works I did. But I think unless you go and see directly the domain expert and how they work, like the whole workflow, the integrity of it, it's a little bit difficult to know that this is a need, and especially if you're more in the HCI community than the Viz community. So that could be one of the reasons. And that's why I think like the whole object manipulation and 3D selection is more explored, because this is a problem also in HCI. So there's more work done with this because it is a problem not just for 3D data sets, but also for 3D objects.
So you talked a little bit about the challenge of evaluations and that you didn't find so many. So I have a question whether there's any investigation about accuracy when it comes to selection, whether anybody compared kind of these 3D possibilities for selection with respect to selecting on a 2D screen with a mouse?
So this, we actually did, in one of our papers, we did compare a 2D selection technique versus a 3D one. But it was for providing in the end 3D selections, right? But there was like a 2D input versus a 3D input. So that's in one of the papers that we did with Tobias as well a couple of years ago. But it's the whole thing with like comparing to other techniques is also a little bit difficult because, as I said, the code is not very often available or reusable correctly. So it's a little bit difficult to find like sometimes the control group you're going to use for your new technique, right? And I think one of the things that's also a little bit difficult when you think about specific domains is how do you define accuracy, right? If you need to select a specific part of a data set and you select a little bit more than this, is it a real problem? How do you define accuracy in fluid dynamic versus astronomical data? Things are unlikely to be exactly the same measure. And when I did personally a study with fluid dynamic, the researchers, they mentioned that the selection doesn't need to be extremely precise. They want to somehow select something around this, and if it's not, if it's a little bit more, then it's fine. They don't really care.
But maybe this could be some subjective feeling. Like I have the feeling I have really a hard time to grasp what I really want to grasp, or to specify a specific area in my volume. Let's
Absolutely
take it from that direction. So is this easier with these?
So totally. I think it boils down to, and it's something that some researchers said that I know that work in for dynamic data visualization. They do say that like what matters for them is that they can do their job efficiently. It doesn't matter like to be precise, to be accurate. This is not really something they're interested in. What they want to do is being able to do it in a potentially more natural way or like an easier fashion than what it used to be, meaning scripts for them, because they had like a mouse keyboard. That was it. It could be a feeling of that. And so when we compare this 2D input versus 3D one, actually the 2D input was augmented by the computer, right? Like so the computer would use some form of measure to augment the 2D lasso into a 3D selection volume. And we compared it with something where you would give control to the user completely. And so what we found out is that it actually takes more time if you give control to the user. So that was a specific technique, right? But it was eventually more precise. So it was something that was kind of interesting. The people were more precise with it, but it took, I think, something like twice as much time to do it. So maybe there's some like what I would looking for is to try and find like some form of hybrid approach where you can provide both. Like in case of like, oh, I just want to select this very quickly and this is very convenient and easy, I can just select like this. This is very nice, but now I need to be very precise, so I want to have control completely. And I think finding this kind of like hybrid mechanism where we have full control to the user or half control, like computer augmented selection, would help.
I have one last question. So given the fact that there's kind of a long learning time until you can have these things, do you have an idea what kind of user groups are eager to use it? Or is it a specific user group? Can you make differences between the people here?
I really don't know. I wish I knew, right? Because then we could just approach people who are very likely to be very interested in it, and we'll get so much more data from it. I'm not sure. It's a little bit difficult to know. I think that's again very, very personal feeling, right? Like this is very subjective. But I think that the people I talk to through like experiences I've done with other scientists, like they either are very well aware of the possibilities, like the younger researchers need to be very well aware of the possibilities of VR and AR and all of this, and they're very excited about it. Or like maybe the more senior researchers are not really aware of it. When you showed it to them, they're like just amazed. But like getting their time is a little bit difficult, right? So it's always a little bit of a mix here. Like I'm not sure there's a correct answer to that question. It's very, very subjective also. Like it's just anecdotal evidence.
Okay, then I would like to thank you again.
Thanks for the question and interaction. Happy to take more questions on Discord if there's more later. It doesn't have to be now.
I think we have to move on to the next talk. So we are coming to the second talk in this session, and this is a state-of-the-art report about data physicalization, topics that also gets an increasing interest in the visualization domain. The paper is presented by Hessam, Djavaherpour, and Hessam, please go ahead and take.
Hello everyone, and welcome to our STAR presentation on Data to Physicalization, a survey of the physical rendering process. I'm Hessam Djavaherpour, and today I'm going to present our work done in collaboration with Faramarz Samavati, Ali Mahdavi-Amiri, Fatemeh Yazdanbakhsh, Samuel Huron, Richard Levy, Yvonne Jansen, and Lora Oehlberg. The physical representation of information is much older than the invention of computers or even paper and dates back to 75,000 BC. For example, a close-up look at this object shows a systematic pattern that represents information rather than decoration. According to Jansen et al., a data physicalization or a physicalization is a physical artifact whose geometry or material properties encode data. Research has shown that physicalizations can improve the efficiency of information retrieval and memorability of data when compared to similar designs shown on flat screens. Physicalizations in fact inherit all of the practical and social advantages of everyday objects. For example, they can be explored through touch, carried around, possessed, or even directly manipulated. Data physicalization has both historic and contemporary applications in many domains, including geospatial visualizations. For example, the work of Djavaherpour et al. On physicalization of geospatial datasets, or the work of Oehlberg et al. For making 3D prints of landscape models, which is called Landscaper. Another application for physicalizations is medicine, and an example for that can be anatomical models 3D printed by Boking et al. Physicalizations can also be used in mathematics, and also there are many applications for them in educational purposes. They can be used for 3D printing molecular models or for showing reaction progress in chemistry education. Physicalizations have also been used in planning and architecture. An example for that is luminosity. Designing and producing physicalizations require expertise in both visualization and physical fabrication. Making precise physical objects that reflect data, such as architectural scale models, has historically been time-consuming, laborious, and costly. Why today's advanced and accessible digital fabrication technologies such as CNC machines, laser cutters, and of course 3D printers have facilitated the process of physical fabrication from digital data, rendering data into a physicalization is still challenging. Today, digital fabrication machines have taken over the process of shaping material into the desired form, but still diverse knowledge is required, from preparing the design files for the machines to considering possible interactions between a chosen design, fabrication techniques, and materials. We call the steps involved in this process the physical rendering process. In fact, rendering is the stepping stone of the process from data to physicalization. In this survey, we want to unpack this transformation and provide physicalization researchers, practitioners, and designers with a review of various physical rendering methods. Physical rendering or rendering makes the visual presentation perceivable by bringing it into existence in the physical world. Rendering in the scope of this research refers to the back and forth process from digital design to digital fabrication and its specific challenges. Physical rendering requires an interdisciplinary understanding of computer graphics, visualization, design, fabrication, and HCI. In this survey, we focus on the rendering phase of the extended EuroVis pipeline by Jansen and Dragicevic and review approaches and methodologies for converting data into digitally fabricated physicalizations. This star aims at addressing the following questions. What is the target dataset and the resulting visualization idiom? What are the dominant strategies toward physical rendering? And what are the challenges of rendering transformation? Many academic and art communities explore the physicalization of data. The question here is, how can we start assembling a corpus of examples in order to be able to do the analysis that we needed? As a solution, we started to build a corpus from a systematic literature search by filtering papers, short papers, and posters published between 2010 and 2020 that met a keyword search. Meanwhile, we wanted to also include examples from broader art and design community, so we headed to datavis.org. In the academic literature, we searched through venues related to graphics, visualization, HCI, and fabrication in art and architecture. Since the focus of this star is on digital design and digital fabrication for rendering, in Datavis and its bibliography, we excluded work from before 1990 as CAD/CAM technologies were less common. Then, we continued to review the collected academic work by checking if the work aims to visualize any type of data. Then we made sure that there is a physical object available as a result. At this stage, we started analyzing both academic work and the datavis.org work together by first making sure that there is a proper documentation that explains the design and fabrication process. Then we had to make sure again that the selected works were made by using any type of digital design or digital fabrication. While a passive object at this point is qualified to be added to the final corpus, we excluded any active physical platforms that did not have specific data physicalization applications designed for them. We will explore active and passive platforms in today's presentation. This made our final corpus of 141 works. Our final sample includes 141 works with 99 works from academia, out of which 78 were long papers, 18 were short papers, and 4 were theses. We had 37 works from artists, including 28 presented on websites and 13 presented as videos. Professional communities such as architects were also part of the physicalization community by making 5 projects presented in papers or on websites. Alright, now that we discussed our corpus curation process, let's talk about the process of physicalization. The process of physicalization includes a range of actions and activities such as collecting data from different types, deciding about the physicalization purpose and approach to physicalization, and digitizing data and converting it into a visual form and fabricating it. To analyze the collected works of our corpus, we coded the data based on the necessary steps towards making a physicalization, such as stakeholders and physicalization applications, visual encoding idioms, goals, and computational power components, digital design and digital fabrication to make the final physicalization. We call all these steps the physical rendering pipeline, in which the first step is target data, where many datasets can be transformed into physicalizations. The data plays a significant role in the physicalization process by starting the impact on the early design decisions to many detailed designs for fabrications. Datasets that were used as target data in our corpus include biological and medical data, statistical data, personal data, geospatial and environmental data, image or videos used as datasets, and other type of data. So there is a table in the paper that you can refer to know more about other types of datasets, and also to know many examples related to each category of these datasets. All right, back to the physical rendering pipeline. The next step in this pipeline is the physicalization purpose. At this stage, designers must identify the user or stakeholders and applications of their physicalizations. Most of the physicalizations in our corpus are designed for the use of general public. However, there are some cases in which physicalizations are meant to serve a specific group of. In fact, 117 of the total works in our corpus were designed for the general public, and 24 works were designed for groups such as experts in the fabrication field, learners of specific groups such as biology or anatomy, visually impaired people, specific industries such as shoemaking, non-experts in fabrication, or chefs. Different applications in a physicalization scenario require different and sometimes unique rendering approaches and decisions. 30 works in our corpus were designed to simplify the understanding of information, such as the PARM project. 16 works were designed to raise self-awareness, most of which focused on physical activity. However, another goal for making such physicalizations has been keeping track of progress during the PhD studies, such as the thesis Lego board. Physicalizations have a great potential for improving accessibility. We have 5 examples from this category, including the perceptual model for tactile roughness. They can also be used for learning and education, such as geospatial physicalization in geography education. Finally, physicalizations may be designed as research and engineering tools. For example, zoetrope can be used for various material design purposes. We had 12 of such examples in our corpus. The next step in the physicalization pipeline is approach to physicalization, which deals with the visual encoding idiom of the physicalization, methods to achieve the physicalization goals, and whether physicalizations should remain connected to the computational power or not. Munzner calls every distinct approach to create and manipulate a visual representation from the abstract data an idiom. The visual encoding idiom controls what people see in a visualization. Based on the physicalizations reviewed in our corpus, a high-level categorization of representational idioms can be introduced as physical charts, such as this scatter plot showing New York City school dropouts, topography, and physical elevation models, both to show elevation data and other datasets, such as this elevation model that shows the average prices of building lots in Germany, informative spaces, and installations. These physicalizations are mostly architectural spaces or artistic installations designed with data for the purpose of conveying a message, such as the Data Specialized Pavilion by Hosseini et al. Such physicalizations are referred to as data spatializations. Please refer to the paper for more details and examples. And finally, we have unique data objects, which are frequently referred to as data sculptures, such as this data clothing that shows air pollution data. Identifying the visual idiom helps the designers to have a clearer vision of whether they can achieve their goals through pragmatic or artistic approaches. We refer to pragmatic visualizations as having the goal to explore, analyze, or present information in a way that allows the user to thoroughly understand the data, and of artistic visualizations as having the goal to communicate a concern rather than to show data. However, this distinction is usually blurry. Examples like a piece from the pie chart use a classical encoding, that is pie chart, in an art exhibition with the intent to draw attention to gender distribution in the tech world. So this work is intending to communicate a concern. At this point of the process, a physicalization designer should have collected enough insights to determine how the work employs computational components and whether it needs to be a passive, an augmented, or an active object. Either of these decisions may require the decided upon visual idiom to be revisited and modified accordingly to better suit the physicalization goal. We call physicalizations that are disconnected from computational power passive. Passive refers to the use of computational power and not the support of interactivity. We have 82 passive works in our corpus. In 14 examples, we observed the combination of passive physicalizations with augmentations such as projections or augmented reality overlays, such as the Emoto project. Finally, we identified 47 examples of physicalizations that are dependent on some form of computational or at least electrical power to show their data to an observer. Finally, after all the initial steps and decisions, it is time to start the rendering process. At this stage, physicalization designers need to prioritize the digital design methods or digital fabrication approaches. In case of having the fabrication techniques prioritized, design methods will be later set based on the fabrication constraints, and in either of these choices, there will be a back and forth step from design to fabrication until the 3D models can be fabricated and, if required, assembled. In this report, physicalization design is the stage of making the abstract visual form and the final visual presentation. When working in physicalizations, visualization designers should consider perception and experience of physical environments, geometric forms, materiality, cultural symbolism, and spatial relationships. Many of these challenges have been explored and practiced for many years in the field of industrial design and architecture. For example, Sosa et al. Have introduced 4 design principles inherited from industrial design that can be applied to physicalizations. They encourage physicalization designers to treat data as a new type of material to design with. Design for reinterpretation of the target data, design for cognitive and emotional engagements with target data, and design to give people the opportunity to use the data to rethink. Hall and Willett proposed the concept of data tectonics to describe the holistic nature of designing physicalizations. Data tectonics in architecture is the interwoven relationship between space, function, structure, context, symbolism, representation, and construction. Data tectonics, on the other hand, is the relationship between context, data, visual representation, materiality, fabrication, and interactions of a data representation, and suggests that physicalization designers borrow from the approaches used by architects for many years, such as design sketching, diagramming, and making scale models. Design is the first stage of the rendering process that applies visual mapping transformation to data and gives it an initial visual form. In this paper, we focus on digital design and talk about various approaches such as 2D CAD, 3D CAD, sketch-based modeling, script-based modeling, and hybrid design. For various physicalization scenarios, a 2D drawing needs to be made either in the form of a vector representation or a raster representation. 2D drawings can be used to make outlines and contour lines for laser cutting. They can also be used for tracing over hand-drawn sketches. For example, in this Motus Forma project that represents people movements in space. 2D drawings can also be used as part of the 3D modeling. Speaking of 3D modeling, there are 3 main approaches for making fabrication-ready models. These approaches are 3D CAD, sketch-based modeling, and script-based modeling. In 3D modeling, 3 primary representations are usually used, which are polygonal meshes, non-uniform rational B-splines or NURBS, and constructive solid geometry. We define a script-based programming as either parametric modeling, scripting in a 3D CAD software, or programming. To ease the process of modeling, many software programs provide a visual programming interface where users connect a series of functional blocks into a sequence of actions. This design solution is referred to as parametric design. Grasshopper is one of the examples used for parametric design and is used in many physicalization examples in our corpus. For example, robotic nails data sculpture or data moray data sculpture have been designed using Grasshopper plugin for Rhino. User interfaces for 3D modeling commonly follow the windows, icons, menus, and pointer paradigm. A sketch-based interface is considered as an alternative paradigm for 3D modeling in which 2D hand-drawn sketches are used in the modeling process, creation, editing, and augmenting the initial model in an iterative manner. Some CAD software and parametric design platforms are also compatible with script-based programming to make custom algorithms for the design of physicalizations. For instance, Hosseini et al. Have used Grasshopper and custom Python scripting to build Portal. In our taxonomy, we refer to such design methods as hybrid. There are many cases in the design of physicalizations where off-the-shelf CAD software and even parametric or hybrid design approaches are not able to handle the complexity of the process of transforming data into a model. In such cases, physicalization designers make their own programs by using available programming languages such as processing, Python, Java, or C++. For example, in Landscaper, the process of transforming elevation data into meshes and also making submeshes for the fabrication purposes was done through programming. Fabrication brings the visual representation into existence in the physical world. The fabrication techniques that we discuss here are 2D printing, additive techniques, subtractive techniques, digital papercraft, and hybrid types of fabrications. We also discuss augmentation methods that are mainly AR or augmented reality and projection, and methods to make active physicalizations. The final stage in the fabrication process is assembly in case it is required for any reason. A trivial technique to bring patterns, designs, and visualizations into the physical world is 2D printing, such as for making customized volvels. Also, using 2D printing in physicalization is one solution to overcome the limitations of affordable off-the-shelf FDM 3D printers. The general concept in additive manufacturing is to build objects layer by layer. One of the most common tools in this category are 3D printers. Over the past decade, 3D printers have become more accessible. Moreover, the possibility of making complex objects by 3D printers have made them a common choice for making prototypes and final physicalizations. Main types of these printers are locally depositing material or FDM 3D printers and solidifying materials or STL printers. We have 62 works using various methods of 3D printing in our corpus. One of the most accessible and affordable 3D printers are FDM printers that make 3D objects layer by layer through heating or extruding thermoplastic or wax filaments. FDM printing has a long history in physicalizing complicated shapes such as macromolecular assembly. We have so many examples of physicalizations made by FDM 3D printers, such as the singing bowl, which is a sonification of blood pressure made by stainless steel printing, or Phantable, that summarizes sports data and user excitement, and even these mathematical puzzles. However, FDM 3D printers come with a series of shortcomings. For example, FDM printing relies heavily on support structures that need to be removed after fabrication. Therefore, to fabricate delicate structures, creative solutions are required, such as layer supports in Ang's et al. Work. FDM printing also suffers from a limited building volume, which requires breaking a large model into printable volumes. Such approach was first introduced by Chopper and then used in many physicalization examples, such as Landscaper. Another shortcoming of FDM 3D printers is their limitations in terms of number of colors. One solution is printing in different but limited colors. Another solution is using projectors and augmenting the model. Layer solidification is a 3D printing process in which the top or bottom surface of the object is solidified from a non-solid material, such as liquid or powder within a tank. Different types are SLA, SLS, binder jetting, or sheath lamination. Although this type of 3D printing still has some limitations, such as the size of the resulting product, it does not need any support structures, which makes it possible to produce delicate physicalizations, such as data sculptures in the form of a tree. However, 3D printing by this technique is usually more expensive than FDM, and the chance of using a wide range of low-cost FDM-supported filaments is missed. Color plays an important role in making understandable visualizations. There are some examples of using different types of color 3D printing in physicalizations, such as for making these type of landscape models, or using a different type of 3D printer to make motion sculptures, or making a 3D texture material. Subtractive manufacturing techniques gradually remove material from an unmachined part by using a sharp cutting tool. Milling is the most versatile subtractive technique with a large variety of materials available for it. One other subtractive method is cutting. CNC is a common method of digital fabrication and physicalization used in 10 projects of our corpus. Toolpath artifacts are common with CNC machines and may be misunderstood by data, such as the grooves on this close-up of wind cuts. This is something to bear in mind when designing physicalizations. CNC machining can be used at various scales, including for room-size architectural scale physicalizations, such as the Daytona Ray project. In cases that a huge number of pieces have to be milled separately and assembled, detailed shop drawings are a must for the assembly process. Cutting techniques are basically a subcategory of subtractive methods. One of the most popular cutting methods is laser cutting, used by 20 works in our corpus, mostly due to its speed, efficiency, and its ability to cut a wide range of materials. Laser cutting have been used by the physicalization community to make 3D bar charts, stacked scatter plots, data sculptures, or even for making parts for active physicalizations such as in polysurface. Laser cutters are capable of etching the surface of different materials and providing engraving. This is quite handy for adding details such as some information about charts' axes. Also, this ability of engraving combined with material properties can be used to make the whole physicalization, such as producing woodblock printing of watercolor paintings. The removal of the material also provides the opportunity to fill the holes with different materials and make novel physicalizations, as in the Green Berlin project. Formative fabrication processes utilize mechanical forces to reshape or deform material. Examples of formative approaches are vacuum molding and thermoforming. A customized example of thermoforming is the computational thermoforming project that introduces a novel method for the fabrication of customized, unique objects. This makes it a useful solution to support color and texture for physical rendering of physicalizations. Another possible solution in the fabrication of physicalizations is a papercraft and origami that is tailored and controlled through programming 3D CAD for fast and accurate folding and assembly purposes, such as in the anatomical edutainer. Slice forms and origami are alternative papercraft approaches that can be digitally designed for the automatic creation of physical models, as used in the Slice and Dice project. In 15 works of our corpus, hybrid fabrication techniques have been used, such as using 2D printing and 3D printing to make physicalization of geospatial models, or using 2D printing and CNC milling to make solid terrain models with airplane trajectory, or using laser cutters and 3D printing to make robotype, or as another example, using 3D printing and CNC milling to make PhysVis. There are 76 works in our corpus that are fabricated in separate pieces and need to be assembled to form the final physicalization. Fabrication constraints such as size limitation force the design to be piecewise in a way that can be assembled to make the final physicalization, which is bigger in terms of scale. Such assembly also provides interaction opportunities. Augmenting a physicalization adds an extra layer of information to a passive object, and it is an ideal method for adding sophisticated interactivity without using actuators or motors. The augmentation approaches in our corpus include projection or augmented reality. However, we only had 14 works out of 141 work that used augmentation approaches. Physicalizations using projection augmentation consist typically of a passive fabricated physicalization with additional data projected directly onto it. They provide a good chance for annotations and interactivity. When using projection augmentation, it is necessary to calibrate the physical object and the projection. Sometimes, the physicalization setup includes a combination of projection and 3D scanning, such as in Tangible Landscape project, which enables the system to recognize the topology of the passive physical model and updating the projected data. Personal augmented reality are technologies that offer an augmented perspective of an object to a single individual. We only have 3 items that make use of AR. It is worth reminding that AR devices must be held, which both limits the use of users' hand and occludes their view of the actual physicalization. Active physicalization rendering techniques are more represented in our corpus with 47 examples, with many falling into the category of data sculptures. 3 main goals for choosing an active rendering technique are supporting changes of a single dataset, supporting multiple datasets, and enabling interactivity beyond what is possible using augmentation approaches. The development of platforms that support physicalization of various datasets requires skills in mechanics, fabrication, sensor and actuator choice and placement, and microcontroller development. Active platforms included in our corpus follow 3 main approaches: shape-changing displays, suspended elements, and robotic approaches. Shape-changing displays are actuated devices capable of deforming in various forms. The most common form factor for such displays are rods or bars arranged in arrays and capable of moving up and down to provide a 2.5D display with an actuator range between 100 to 1000. They usually show data that could be represented by a 3D bar chart, resulting often in a resolution of 5 to 10 millimeters per actuator. The relief prototype uses a similar principle, but connected the individual actuators with a cloth such that a smooth surface is created. Interactions are made possible by a depth camera and interpreting people's gestures. Unlike two-dimensional on-screen visualizations, or visualizations in virtual reality, physicalizations are bound to the laws of physics. There have been, however, a few attempts to overcome these limitations, such as using strings or ropes to suspend and actuate sail-like structures. Few have attempted to suspend elements without any support, such as floating charts that uses ultrasound to control the position and movement of small and lightweight objects within the range of their actuators. Few examples in our corpus have used robotic arms to assemble physicalizations. While the overall rendering platform can be considered active, but the resulting objects, once assembled, are passive objects, such as using the KUKA industrial robots for string arts. But an entirely different approach was taken by Lecoq and colleagues who developed a platform of small robots they called zooids. Each of these robots meant to represent one data point and to move around the surface to make a truly active physicalization system, capable of showing many different datasets. The rendering process is a skill-oriented approach. In order to overcome this issue, some research has been undertaken with the goal of automating the whole or parts of the physical rendering process. MakerVis is one of the most inclusive platforms developed for this goal that is capable of automating the whole physical rendering process from data filtering to physical fabrication. Finally, physicalizations may go through a series of evaluations and user studies, which may result in the iteration of the process at various steps, including revising the physicalization approach or revising design decisions and fabrication techniques. And this concluded the physical rendering process. Here, we have also illustrated the schematic depiction of the distribution of taxonomies in our paper. Here, we briefly list some of the challenges in the rendering process, and we start with data-specific challenges. Pre-processing datasets plays a very critical role in defining the overall shape of the physical model. This is particularly true for scientific datasets, mostly due to the number of data points and the overall complexity. Another key data-related challenge is identifying a representational idiom that best matches the data features. To make the best decision about the appropriate idiom, data plays a critical role. Also, design and fabrication decisions are critical towards this goal through meetings with experts in the design field and meetings with end users, as they may sometimes prefer an idiom over another one. An example is the preference of people to have the frog-like representations over the classical charts to learn about their activities. The physical scale influences the fabrication technique. For instance, in order to make larger physicalizations, decomposing the model is necessary, which requires assembly instructions. Small physicalizations are usually constrained by the resolution of the fabrication technique. For example, FDM printers cannot make features smaller than their extrusion head. Prototyping facilitates the iteration and the iterative design, and it can be done through simulations such as using the Congru plugin for Rhino to simulate movements in active physicalizations, or through physical prototypes that can be either a small portion of the final model, such as these trees for the landscape project, or it can be a low-fidelity prototype of the whole final physicalization. While, regardless of the scale, we can call any physical artifact representing data through its geometry a physicalization, all the past works on data physicalization focused on scales that are either graspable by humans or do not go beyond room scale. Room-size physicalizations require a dedicated space for the audience in order to enable them explore the model. Assembly, as mentioned earlier in this presentation, provide the chance of interaction for people, regardless of the design approach that can be either constructive physicalizations, participatory design, or other types of physicalizations. Although many impressive works have been done in this field, many areas of rendering physicalizations remain rather underexplored. For example, there have been many creative fabrication methods introduced by the computer graphics community with great potential for physicalizations, especially for dealing with the issue of color and texture. By applying such methods to physical rendering, many interesting possibilities will be introduced. Also, numbers in our corpus show that physicalization has been slightly underexplored in the scientific community and for pragmatic purposes. Many interesting aspects of physical rendering in artistic physicalizations and interactive installations have strong potentials to be applied to scientific works as well. As mentioned earlier, very few efforts have been made to develop augmented physicalizations. With the increasing popularity and technological advances of devices that support augmented reality, physicalization designers should take advantage of such approaches and creatively overcome the existing issues. And another underexplored area in this field is the automation of physicalization rendering process. Currently, there is only one work, which is MakerVis, that aims to automate the whole physical rendering process for non-expert users, which supports limited rendering approaches. Software such as MakerVis can be further developed and become the CAD of physicalizations. This concludes our presentation. Thank you so much for watching, and we're now happy to take questions.
Thank you, Hessam, for this really inspiring talk. I'm impressed how broad and rich this field actually is.
Thank you.
During your talk, you answered almost all questions that I had in mind, so I almost have a hard time to ask questions now. But still, I think we all think that's really cool to have the possibility to hold our data in the hand. However, this is some effort to get there. Are there any guidelines on kind of what data would be worthwhile to be really produced? And so kind of how do I decide which data to pick when it is worth to take the effort?
Okay, yeah, that is a very good question. I guess it depends on as you mentioned, it depends on the type of the data sets that you want to go through this effort. For example, geospatial data is usually complicated. The scale of it is, usually it's a big data set, and sometimes it's really difficult for users that are not experts in that field to understand that data fully. So it's kind of depends on the type of data set. As I mentioned, geospatial data is a good example because it's complicated, it's huge, the scale that it covers is really big. And it also depends on the type of audience that you want to work with. So sometimes you have non-experts in a field. For example, for teaching to students in high schools, when you want to teach geography, geospatial data, when it is made physical, it can be more graspable for them. So it's really worth going through all these efforts to do that.
But should I rather pick a simple example, or should I pick something that is more complex, that can show more feature? So people don't have the chance to produce something so that people start learning to interpret it, and then I come with the real data. So seems to be like a really hard decision at which level of complexity I would pick my data.
Yeah, it is tough to decide about that, but sometimes there are some examples that you have a limited time and resources to teach a kind of data set to an audience, to let them know how it works. So if we compare that with on a screen digital visualizations, for example, as I mentioned in geospatial data, when you want to teach a topic to a group of users through a digital platform, you first have to teach to them how to use that platform. For example, for the concept of overlaying different data sets in GIS, you need to teach them how to use that software, how to use that tool in order to be able to go through the concept of overlay. But when it comes to a physical world, the concept of overlay is something simple. You have some layers, physical layers, you can stack them atop and then explore what happens through overlaying different types of data sets. So these are some points that we can use to decide about, whether we go through all these, series of design and fabrication or not.
So here I have a very long question from Discord, so I will read it to you. It's from Renata. At first, she wants to thank you very much for the great talk, and she has two questions. At first, data physicalization is not a new field, and in one way or another, physical objects have always been used for conveying the underlying data. In the last few years, the field has seen an upsurge. So why now? What is data physicalization now? Why is it more timely now than before?
Great question. We mentioned this in the paper that, yeah, making physical objects is not something new. It even goes back to 7,000 years before Christ. And it has been around in many fields, like architects, as long as we remember, they used to make scale models of their work, even after the invention of modeling software. But in recent years, because digital fabrication tools have become more accessible, more powerful, nowadays everyone can afford to buy a 3D printer and start making objects with that. So this is a great reason that data physicalizations have become more popular in recent years. Before that, all the fabrication process used to be done by hand, and it used to be laborious. So sometimes people wouldn't do that to make, a data physical. But nowadays, you have a lot of accessible digital fabrication tools, and it really helps for this field to be more practiced and more well-known.
There's a second question from Anata. So in medical data physicalization for the general public, there could be the dilemma of keeping it either accurate or entertaining and pleasant.
Yeah.
So what is your view on that? How to achieve a balance between the two?
It is a very good question. I guess it depends on the end user of that medical data. Sometimes we want to present some medical data to general public. For example, it's about your health, it's about your activity. You want to know how your body is actually feeling based on what you're doing on your day-to-day basis. So in that term, it used to be engaging, it used to be simple, and it should be a form that can be easily understood for the general public, because it's about their own health and they are not experts in the field. But sometimes you want to make physicalizations for the experts in the field. For instance, there is a project, they are working on making physical objects of a special bone structure on the head. So they are making this data physicalization for surgeons. So they are experts in the field, and what is important here is, having the physical object matching the real data as we can do it in the best way. So in terms of balance, in terms of weight, in terms of representing the data as accurate as possible, this is the goal that we have to have in mind. So it kind of depends on the user and who we are making that physicalization for.
Thank you. There are two questions from Legao. The first one is, are there specific methods about fabrication and the assembly process, or does it depend on different techniques that you will use?
I'm not sure what they mean by specific methods about fabrication and assembly process. Deciding about different fabrication techniques, as we mentioned through presentation, and we have also mentioned it in detail in the paper, depends on a lot of factors. It depends on your data set. It depends on the type of visualization, visual idiom that you want to choose, your end users, what kind of digital fabrication tool you have to use. So these are factors that you start thinking about when you want to decide about the digital fabrication tool. And then based on that fabrication tool, you whether need to have assemble pieces or not. And also the physical scale of the object that we make with a tool that we have in hand plays a critical role in deciding about assembly or not. As I mentioned, if you want to make a big model of a landscape, for example, using 3D printers, FDM 3D printers, they have limited building volume. So you have to start cutting the model into pieces, and then assembly is something that is inevitable. So it kind of depends on what route you're taking, what fabrication tool you use, and then the assembly is sort of dictated. Another reason for having a model to be assembled is sometimes you want to start from scratch and design your physicalization in a way that produces the chance of physical interaction for your end users. Because as I mentioned in the presentation, this assembly process is not always because of fabrication constraints. It also is a chance for end users to start, interacting with data. So sometimes you may want to do that, but because interaction is so important for your design. I hope I could answer the question.
The second question would be, do you have any insights about effective evaluation metrics about applying to data physicalization?
Effective evaluation metrics. Evaluations, there have been a lot of different research about evaluating physicalizations. They have been evaluated in terms of how accurate they are in terms of representing data, for data retrieval, for improving the memorability of data sets. So these type of evaluations are kind of used to see if your physicalization is, let's say, successful for the goal you are going to take. And sometimes another type of evaluation metrics are about the design decisions and fabrication decisions that you have taken. As I mentioned in the process, there are a lot of cases that after the evaluation, you understand that the design decisions need to be modified, need to be revisited and changed. For instance, we had a work for making some educational tools for high school students. The assembly process for that work was based on some codes for each piece, and the codes were, were unique codes, and the shape of each piece was unique. So it was difficult for students or for the teachers to assemble this model. After the evaluation, we understood that we should make the pieces modular so that the order of them is not important. In that limited time frame that they have in their classes, they can just start putting all the modules together and have their model ready, because the data overlay concept was more important for them. So these are type of lessons that we can learn from evaluations, and we can improve our designs in physicalizations.
Thank you. So I have a very different topic here now. And that's coming from Lonni. He is kind of worried about the impact on the environment. And he asked whether you have seen any papers mentioning the potential environmental impact, since you're making many hundreds, thousands of objects. Yeah.
It's a very good question. There was one work when we were reviewing this whole corpus of different physicalization work that started using water jet to make their object, their physicalization. So they mentioned this environmental impact of physicalization there, that water jet doesn't seem to be a good solution, because the material, the water that is used, is not recyclable. And then when you want to wash out the residual of material, the type of material that needs to be added to that is something that again cannot be recycled. So there are some fabrication cases that in those fabrication tools, and using those fabrication tools are not environmental friendly at all. But yeah, but in terms of 3D printing, I myself have been thinking a lot about using filaments that are recyclable, and this can be a good research topic. I'm not sure if people have started doing that, because there is a lot of material science included. But I've always thought about being able to use the extra filament that is used, the residual of the support structures, for example, in FDM 3D printing, and use that again and bring it into life, and making new filaments to make the process be more environmental friendly and more recycling the material. But yeah, this is something that we need to think about it, and to make our impacts as less as possible.
So I have one last question from my side. So it seems like physicalization is really an interdisciplinary process, and you have to have a lot of different knowledge in all these stages that you mentioned here. So do you have any advice for me as somebody coming from visualization? So how to get started?
Great question. So people coming from visualization are experts kind of in the field. So what they need to know is just focusing more on the fabrication part of the story, and also on the modeling part of the story for making designs. The physicalization work that we reviewed in our paper, where we were focusing on digital design and digital fabrication, but that is not the area of physicalization is broader than that. You can start by using simple tokens or hand-woven structures, or very simple materials can be used to start the physicalization process. Because as I mentioned, a very good example of physicalization is just making physical bar charts. And for making physical bar charts, you can have some tokens and start playing with that. So not necessarily all the physicalization, all the people who want to work on physicalization need to know digital design and digital fabrication. They just need to know, basic concept of visualization, that, as you mentioned, the type of data that they are going to do this effort and start, physicalizing it to be engaging, and as soon as you start making a physical bar chart, you just realize that how more graspable the data is represented through that. So a good starting point, I would say, is just going, with tokens and simple physicalizations that not necessarily are made through digital fabrication. But then when you become more interested maybe in that field, you can start learning about fabrication and digital design to make models and digitally fabricate them. Maybe it can be a good starting point.
Yeah. Thanks.
Thank you.
I would like to thank you again for this very interesting talk.
Thank you so much.
I want to thank both speakers of the session again, and say goodbye.
Thank you so much. Have a great day. It was a pleasure. Thanks.